Hello guys, welcome on Tesla Adventures. In this video we are going to discuss the Stokes law and terminal velocity. So what is Stokes law? So we can see that if a ball, which is a spherical ball, is moving in a viscous liquid with velocity v, then the viscous force acting on the ball will be given by Stokes law, and Stokes law says that viscous force is neta 6 pi neta rv, where neta is the coefficient of viscosity of liquid, r is the radius of the spherical ball, and v is the velocity with which this ball is moving. And let me also tell you that this formula is only applicable for spherical balls only. If the moving object is of some different shape or size, then we cannot apply the Stokes law on that object. Okay, and viscosity calculations for such objects is not in the curriculum of JEE. So first of all, let us see that what is terminal velocity. So let us see that in this situation, there is a ball which is having a density sigma which is greater than the density of liquid rho, and this ball is being released from rest in a liquid of viscosity neta at t is equal to 0. So at this point of time, mg will be acting in the downward direction and buoyancy will be acting in the upward direction, and obviously mg will be greater than buoyancy due to the fact that sigma is greater than rho. So this ball will start to move in the downward direction, and the acceleration of the ball will be in the downward direction. Now as ball will move, mg will again be acting in the downward direction, buoyancy will be acting in the upward direction, and due to the velocity of the ball, the viscous force will be acting in the upward direction on the ball. So let us write down the equation of net force acting on the ball, that at time t is equal to t, we know that mg minus buoyancy minus viscous force will be equal to ma, and mg minus buoyancy minus 6 pi neta rv will be equal to m dv by dt. Now to integrate this term, let us assume that this is a and this term is b. So a minus bv is equal to m dv by dt, and dv upon a minus bv will be equal to dt upon m. Now the integration of both the terms on the both side, and the limit will be from 0 to v, and time limit will be from 0 to t. So we can see that the integration of this term will be ln a minus bv and divided by minus b, and the limit will be from 0 to v, and on that side it would be t by m. So this is t by m. So ln a minus bv by a, we have substituted the limits, and this will be equal to minus bt by m. So ln 1 minus bv by a is equal to this is minus bt by m, and 1 minus bv by a will be equal to e to the power minus bt by m. So v will be equal to a by b into 1 minus e to the power minus bt by m. Now this tells that the velocity of the ball will be exponentially decreasing, and this will be the graph, and the value of this vt will be equal to a by b. Now let us see that why this is happening. So let us suppose that initially mg minus buoyancy is 100 Newton, and therefore the net force acting on the ball initially is in the downward direction, which is 100 Newton. So due to this net force, ball will start to move in the downward direction, and as ball will attain some significant velocity, viscous force will start to act on the ball in the reverse direction. So this viscous force will decrease the net force acting on the ball in the downward direction, and hence the acceleration of the ball at some later time a dash will be less than the initial acceleration due to the lower net force. So as the acceleration of the ball is decreasing, but its velocity is still increasing because ball is still accelerating in the downward direction, although its acceleration has decreased. So its velocity will be increasing and the viscous force will keep on increasing in the reverse direction. So a time will come when the net force acting on the ball will become zero, and at that time, till that time, the velocity of the ball was increasing continuously, and at that time the velocity of the ball was maximum. Now after that time, as velocity becomes constant, viscous force will become constant, and as viscous force is just cancelling out mg minus buoyancy at that value, so it will always keep on cancelling those mg minus buoyancy, and the net force acting on the ball afterwards will be zero forever, and ball will keep on moving with a constant maximum velocity, which is called as terminal velocity. This is the terminal velocity. So the value of this terminal velocity is a by b. So a by b, let us now substitute the value of a. A was mg minus buoyancy and b was 6 pi neta r. Okay, so value of mg, and now mg can be written as v rho g, v sigma g, and this is 6 pi neta r, and the volume of the ball is 4 by 3 pi r cube g sigma minus rho upon 6 pi neta r. So this will give us the terminal velocity, v terminal, as 2 by 9 r square into g into sigma minus rho upon neta. This is the terminal velocity. Now if in case you forget the formula of terminal velocity in the exam, so you don't need to derive it in such a long derivation. You can do an alternate method, which is a shorter method, but this method is only to derive the terminal velocity. So we know that at when v is equal to v terminal, net force acting on the ball will be zero. So mg minus buoyancy will be equal to viscous force, and mg minus buoyancy will be vg into sigma minus rho, and viscous force is 6 pi neta rv. Now v is 4 by 3 pi r cube g, and this is sigma minus rho, and this is 6 pi neta rv terminal. So by cancelling these terms, v terminal will be 2 by 9 r square g into sigma minus rho divided by neta. So this is the alternate method to find out the terminal velocity directly in the exam, if in case you forget the formula. And in the case of a air bubble, so if a air bubble is inside a liquid or water, then obviously we know that the density of air is less than the density of water. So the terminal velocity will be negative, and which means that this air bubble will rise in the upward direction instead of going down. So you must have seen that air bubble generally rises from the bottom to top of the vessel containing water. So this was it in this video, and this was the last video of viscosity, and in the next video we'll be bringing some numerical problems on the viscosity. Then afterwards we'll start the surface tension. Thank you.